Hello and welcome to CE 3105 Mechanics of Fluids. I'm Venki Udamari, the instructor for this course. And in today's lab, we will talk about hydrostatics. We'll be performing an experiment, two experiments as part of this lab. Both these experiments deal with various aspects of hydrostatics. In the first part, we'll be looking at Archimedes Principle, and in the second part, we'll be looking at forces on a planar surface, or hydrostatic forces on a planar surface. What is hydrostatics? Hydrostatics deals with water when it's red, so hydro stands for water, and static stands for something that's at rest. So while we'll be predominantly be talking about water and hence hydrostatics, the concepts that are presented here are equally applicable to other fluids as well. Okay, so when I say hydrostatics, it can interchangeably be used with the words fluid statics. Okay. Hydrostatic analysis is not only useful when we have water at rest, but we also use hydrostatic analysis even when the water flows. That's because the hydrostatic conditions sometimes can give us a worst case scenario, which is useful for design. For example, the water in the reservoir could move up and down, or there could be flow in and out of the reservoir, but assuming that the water is there at a certain height helps us design that structure. So we often design assuming that there is stagnant water at a certain height when we're designing a reservoir. Water, as you know, as we talked in the last class, has to be in a container. It doesn't have a shape of its own. So water exerts pressure on the walls of the container in which it's present. So understanding the forces exerted on the wall is important for design as well. For example, if you're designing an above ground water structure, like a water storage structure, an above ground water storage tank, then we need to know how much force is exerted by the water that's stored in that tank to ensure that the material used to design that strand can withstand those forces. We also place objects in water, and when we place objects in water, for example, ships, buoys, or any other structure like that, these objects experience an upward force known as a buoyant force, and buoyancy is an important, has many useful applications in the fields of engineering. So in today's class, we'll be looking at forces on planar surface as well as buoyancy. So our goals today are to understand buoyancy and to understand forces on planar surfaces. So we'll start off with buoyancy. The story of buoyancy goes back a long time ago, sometimes in around 250 BC. Archimedes of Syracuse made a very profound discovery, and the discovery was that when an object is fully submerged in a fluid, the volume of the submerged object equals the volume of the displaced fluid. So if we take an object and completely submerge it into a fluid, obviously the water level rises, and then the volume of the water that is displaced by the fluid is equal to the volume of the fluid. So this is known as the Archimedes Discovery, and one of the implications of Archimedes Discovery is that we can use this discovery to find the volume of irregular shaped objects as long as they're submersible. So if we can submerge this object in a fluid, the volume that is displaced, and measure the volume that is displaced, that volume will be equal to the volume of the fluid. The Archimedes discovery led to the Archimedes Principle, and the Archimedes Principle states that when an object is either partially or fully submerged in the fluid, it experiences an upward buoyant force, and this upward buoyant force is equal to the weight of the fluid that's displaced by it. So if we look here, let's say our initial water level is at this line, then we place a fluid. That fluid can either be submerged in water, as I show here, or can be floating on the water. Regardless, there is an increase, or there is a fluid that's displaced. and let's call that volume of the fluid that's displayed as V sub F. So V sub F times the density of the fluid times the acceleration due to gravity will give us the buoyant force. Okay, so the buoyant force is equal to the weight of the fluid that's displaced, and the weight of the fluid that's displaced is equal to the volume of the fluid that's displaced times the density times the acceleration due to gravity of the force. The upward buoyant force acts on an object regardless of whether it's fully or partially submerged in the fluid. So as long as the fluid, as long as the object is in contact with the fluid surface and it displaces water, then we know that buoyancy is acting on it, or it's being acted upon by the buoyancy of the fluid. So if we take a look at the hydrostatic forces of a submerged object in closer detail, so here I have a cylinder, and let's say that cylinder, there is a pressure exerted by the fluid on top of that cylinder, and similarly there is a buoyant force, and that pressure increases with height, obviously, and then there is a buoyant force that is trying to push the cylinder. So if we look at a free body diagram, the buoyant force is trying to push that cylinder up, and the weight is trying to push that cylinder down. So if the buoyancy is greater, then the cylinder or this object will feel an upward thrust and start rising. On the other hand, if the weight is more than the buoyancy, it will start to sink or move downwards. So the buoyancy minus the weight of that object can be expressed as the density of the fluid minus the density of the object times the volume of the object times g. So again, we know that the buoyancy is equal to the weight of the fluid displaced, so don't confuse that weight of the fluid displaced with the weight of the object. They are two separate things. And then similarly, knowing the density of the fluid and the density of the object, we get V naught over g. Clearly, if rho sub F, which is the density of the fluid, is greater than the density of the object, this is positive, so the buoyant force will be greater than the weight of the object. Similarly, if the density of the fluid is less than the density of the object, this parenthetical term here is going to be negative, which would mean that the weight of the object is more than the buoyant force. So what happens when we have a floating object? When we have a floating object, the volume of the water that's displaced is not equal to the volume of the object, because the entire object is not immersed. So the volume of the volume that is displaced is equal to the volume that is immersed in that fluid, and not the total volume of the object. Nonetheless, what happens here is that the buoyancy is trying to push this object up, gravity is trying to pull that object down. So the object is balanced, which means that the weight of the object minus the buoyancy minus the weight of the object is equal to 0. Or in other words, the buoyancy is equal to the weight of the object. The weight of the object is nothing but the density of the object times the volume of the object times acceleration due to gravity, and that's equal to the density of the fluid times the volume of the fluid times the acceleration due to gravity. So the volume of the object to the volume of the fluid that's displaced is equal to the density of the fluid times the density of the object. So we can still calculate the volume of that irregular object, but in this case we will need to know the density of that object and the volume of the fluid displaced. So we simply cannot find out the volume of the object by knowing the volume of the fluid that's displaced. Clearly, the volume of the fluid that's displaced in case of a floating object is equal to the volume that is submerged in that fluid, and not the entire volume of that object. So to kind of recap, when we have a floating object that's partially submerged, the weight of the object is less than the weight of the fluid that can be displaced by that object, obviously because not all of that object is immersed in water or in the fluid. The volume of the displaced water is less than the volume of the object. And then the weight of the liquid displaced by the partially submerged object is equal to the weight of the object. So we can calculate the weight of the object, and from there, knowing the density, can back out the volume of the object, but without the knowledge of density, we cannot get the volume of the object. For something that is floating and fully submerged, the weight of the object is equal to the weight of the fluid displaced by the object, and then the volume of the displaced water is equal to volume of the object. So the difference between here, you notice, is that the weight of the liquid displaced by the partially submerged object is equal to the weight of the object, and then the same thing holds here. Weight of the fluid displaced by the object is equal to the weight of the object, but the volume displaced is also equal to the volume of the object. What if something sinks? Then clearly the weight of the object is greater than the weight of the fluid displaced by the object, and the volume of the displaced water is equal to volume of the object. So as long as it's submerged, even if it sinks, the volume of the displaced water is equal to volume of the object. Nonetheless, in this case, the weight is greater than the weight that's displaced by the object. So clearly the weight is greater than the buoyancy. So as a result, the object sinks. The second part of the class, so in the first part of the class, you will be looking at Archimedes Principle. We'll be looking at various different objects, objects that float, objects that sink, and then we will make use of those formulas and the Archimedes Principle to calculate the volume in case of a submerged object, or the weight of the object in case of a partially submerged object. The hydrostatic forces on a plane surface. So again, if you look at the surface here, let's say this is a reservoir, so we have a surface here, and then there is a water body sitting here. This water is trying to push on this planar surface of width L and certain height here, and those are called plane surfaces. So similarly, you could have an object sitting here. It's got three different plane surfaces, and you can see that the water is exerting pressure or exerting a force on all the plane surfaces that's in contact with. So if there is a planar surface that's in contact with the fluid, that fluid will exert some pressure on that planar surface. And if you are trying to store this fluid, obviously this planar surface must be able to withstand the pressure, or the weight that this planar surface has must be able to resist that force that's being exerted on it by the fluid. So if we could have, for a plane surface, we could have two types of situations. We could have a partially submerged surface. So as you can see here, this is the planar surface. This is where the fluid level or the water level is. The pressure here is equal to gauge pressure, which is equal to the atmospheric pressure. And then the pressure increases linearly with depth. So at the bottom point, the pressure is equal to the specific weight times the height of the water column. So at any place, we can calculate the height of the water column above it and then calculate the pressure. Typically, when we do engineering calculations, we don't deal with the continuous pressure profile. Instead, we put a resultant force or a resultant pressure at the centroid of that surface, and say that that's where the pressure is acting. Clearly, this planar surface need not be, the force always acts perpendicular to the planar surface. However, the planar surface need not be at a right angle to the water column. The planar surface could be at an angle, so we still have water column sitting here, and this plane is inclined at an angle theta, and then of course this force will, if you want to look at the horizontal and the vertical plane, will get resolved into two forces. There is a vertical force as well as there is a horizontal force acting at rectangles to each other. So we can resolve this F sub r into two forces, okay, and then work with it. So planar surfaces are plane surfaces that they actually go in and out of that the surface that I'm showing, so they can be extending into that into the wall in that direction, and there is a force being acted on it, or the pressure being acted on it. And to recap, pressure is nothing but force over the area. So the center of pressure is defined as the point in a plane at which the total fluid thrust can be said to be acting normal to that plane. So we say if we were to represent this pressure distribution using a single resultant force, then we say where do we place that resultant force? We place that resultant force at the center of pressure. The force of water can be computed, as I said, by multiplying the pressure with the cross-sectional area that's normal to that plane. So in today's lab, we will use a hydrostatic bench, and we will use the hydrostatic bench apparatus to calculate our forces. So essentially what we have is we have a pivot point here, and we have a planar surface that's right here, and we want to know what is the force this column of water exerts on that planar surface. So the way we are going to do this experiment is we are going to add water to this reservoir here, and as we add water, the water will start to create a clockwise movement or try to move this in this direction, and we are going to counterbalance that by putting weights on the other side. Again, knowing the distance z and the weights that we have added w, we can calculate the moment in the counterclockwise direction, and that's going to be equal to w times z. And of course, we can balance that force by taking F sub v times x, which is the moment along that axis. So again, we can say that this vertical force acts at a distance of 3b over 8, b being that total distance. Again, that is strictly true as long as the water is not submerged, but we can approximately take that as even when as a first order approximation when we have this plane fully submerged. So when the water level rises and gets to this point above this plane, we'll say that this plane is fully submerged. Okay, so we will be using the principle that under hydrostatic conditions or under static equilibrium, the moments acting should be equal. If there was a net imbalance in the moment, this apparatus will be tilted in one direction or the other. So if you have fully submerged conditions, as I said, under fully submerged condition, this is the planar surface, and the planar surface is fully submerged under water, so there is water above this top of this plane. The moment is related to the height of the water measured from the top datum or measured from that pivot point. So we have a ruler here, and we're going to use that ruler to measure the height of the water. And if we plot the moment, which is equal to W times Z, as I showed you before, which is W times R3 here, if I plot that moment versus the height, I'm going to get a line with the slope equals gamma W W over 2 R square R2 minus R1, where this W is equal to the breadth of the plane, which is given to you here as 75 millimeters. So again, this figure shows R1 and R2, and the distances of R1 and R2 are given to you in your handout. So we can use the handout R2, R1. We know that W, which is the breadth of the plane, which is also given to you, and you can calculate M. So the only thing you don't know here, and for various H, the only thing you really don't know is the specific weight of water, and you're going to calculate that specific weight of water using that slope equation. So once you get the slope, you can plug in the remaining things and calculate the specific weight of water. So that is plotting this chart and calculating the specific weight of water is what you will do with data collected under fully submerged conditions. And when we have partially submerged conditions, as I'm showing you here, this planar surface is only partially submerged with water, so there is going to be a pressure acting in that direction. And again, we counterbalance, we add weights here to counterbalance so that our theta term becomes equal to 0, in which case the cosine theta and secant theta both become 1. So we can calculate again M. and here you will see that m is proportional to h cube, or the height of the water, which is again measured from the top datum, which is where that pivot point is. So if I plot m plus gamma w wr2 square h over 2 over h cube, I should see a straight line showing up like I show here. So part of this experiment, you're going to plot this term versus h cubed to get this line, and show that and prove that how close we got to the theory by measuring the coefficient of determination of this line, or the r square of this line. So in closing, understanding forces exerted by the fluids is essential for various engineering applications: the civil engineer's design of dam, integrity of water storage structures, and then so the plane of the pressure is critical to understanding. The plane of pressure is critical to understanding the forces of fluids on partially or fully submerged objects. So in today's lab, we're going to show that the moment is proportional to the height of the water in case of a fully submerged surface, and the moment, or a function of that moment, is proportional to the cube of the water in case of a partially submerged surface. So that's what you will experimentally determine in this lab. And the first half of the lab, we are going to look at Archimedes Principle and calculate the buoyancy, or the buoyant force. Again, buoyant force is what keeps ships from floating on the river, whereas that object of the same weight can technically be completely submerged or sink down to the water. That's because it's not displacing a lot of volume. So the volume of the water displaced is equal to the volume of the submerged portion of that ship. So by displacing a lot more water, the ships are able to sink, whereas a steel object that has a much smaller volume is going to sink under its own weight. So the experiment again has two portions. One is calculating the buoyant forces, and the other is understanding the plane of pressure and the forces on a planar surface under submerged and partially submerged conditions. Thank you.